Okay, so we just solved earlier the growth rate formula for a fixed rate when all of the r's were the same. That's a fairly straightforward solution. But what happens when the rate isn't fixed? And so the question is, can we come up with an average way to kind of approximate the value? So the first way that they have us do that is if you have a set of numbers, a set of rates from a set of years, like we do in that first example, you can just take the average mean of it. So you can sum up all the rates, divide by n, and you get a number. And as Dr. Tsay pointed out to us, that the average mean generally overestimates performance. And so people decided, mathematicians determined, that a geometric mean is a better average. So let's apply the geometric mean then. So the question we're asking, and we got to come back to this geometric mean, is there a number to the nth power such that the sum of all those numbers, that the product of all those numbers is equal to the average number raised to the nth power? So we want to solve this equation. So the final value, we want to find some sort of average rate, some average geometric mean that when raised to the nth power, just like using this equation here, is the same as a0 times 1 plus r1 times 1 plus r2 times 1 plus r3 times 1 plus rn, where all these r1 to n's are varying rates. And if you go back to here, if you remember from our initial derivation, we had the 1 plus r at the end of the first year, the 1 plus r at the end of the second year, the 1 plus r at the end of the third year. And this could have, well, instead of the r being fixed, these all could have been different. So this could have been 1 plus r1, 1 plus r2, 1 plus r3. And that's what we're looking at over in this equation here. So if you take a look at these two equations, we want to find, hey, is there some sort of r where I can make the left equal to the right? So the first thing you might notice is that the a zeros on each side cancel each other out. They go away. So we're left with this equation right here. So we have 1 plus r to the nth power plus all these other 1 plus r1s, r2s, r3s. So we're going to look at this and solve it using the geometric mean. So if you remember the geometric mean, we have this this equation here that a bunch of numbers multiplied together is the same as this one number raised to the nth power. So here, in this particular case, if you treat 1 plus r as that x, and all of these other numbers as the sum of x's, you'll find that you can write this equation as 1 plus r to the nth power equals to the product of all these numbers added together, which is exactly our geometric mean, right? That's exactly this equation right here. So in order to solve for this, we have to take the nth root of both sides. And now we have 1 plus r of this number equals to the product of all these numbers to the nth root. And if you look back at our geometric mean, this is precisely what the geometric mean is. It's the definition of it. So in Excel, geometric mean, there's this function that calculates the geometric mean. And quite literally, we're just going to use the geometric mean in Excel to match this value right here. So the last step of solving this is that we have a 1 plus r mu, and we're going to subtract 1 from both sides, and so we get this equation right here. So this is where the 1 plus in Excel come from, and the minus 1 in that one example. So the literal Excel definition is geomean 1 plus the cell range, because those are all your individual rates, minus 1. And just to maybe make it a little bit easier, we're going to hop over here to Excel, and we'll look at our S&P history and compare that to what we're looking at here. Here are all of the individual R's that we're looking at. And that's what this cell range is right here. And so we're doing the 1 plus all these R's, and then that's where the minus 1 comes from. Okay, so a couple other things that are important. Some of you may have noticed that, hey, we're doing 1 plus a cell range. Like, that doesn't make sense. Don't you have to do 1 plus each of those cells? And this is a concept called promotion, or adding a scalar to a vector. And computer programmers who are doing data analytics came up with a solution for this, quite frankly, because they were lazy. And nobody ever wanted to type this, 1 plus A1, 1 plus A2, 1 plus A3. So they came up with a shorthand way to do it and just said, hey, if you ever take a number and add it to a range of cells, I'm just going to go ahead and assume you wanted to add that number to all of the cells. And that is, in fact, what you do. In earlier versions of Excel, you have to tell Excel to do that promotion. So I'm using Office 365. So you don't have to do it. But if you're using a different version of Office, then you do have to put in the brackets. Or you can do the Command-Shift-Return that Dr. Tsay showed us. And so incidentally, for those who are interested, the same holds true for a matrix, right? You can actually do not just a column, but an entire range of cells, column and rows, and have that promotion. Incidentally, it's not just addition of a scalar. You can also do multiplication of a scalar. And we're going to look at that here next. The last thing to look at here is the Excel function in terms of the deterministic analysis. The geomean function, it just calculates the products and takes the nth root of it. So in our particular problem that we were looking at, this here is 1 plus all of the rates that we looked at in this equation over here. The other value that we're going to use is the future value. So this here was kind of an important function and had some confusion. It turns out that a lot of the equations in Excel are designed for loans and payments. In this particular problem, we actually have deposits, not payments. If you read the help function, which I'll show you how to do in the next video, you'll see that when it's describing the payment field here, it says that this is the payment made each period, and the present value is the lump sum of future payments. And payments are traditionally negative. So if we want deposits, we have to negate a negative, which is just a negative, adding in a minus sign. So the way we did that in the when solving the problem was that we added in a negative in front of the annual payment we were making and a negative in front of the principal amount. So these are the reasons that those negatives appear in the future value calculation that we do in Excel. All right, enough theory. In the next video, we are going to look at some of these concepts in Excel itself. And then the video after that, we'll actually go through the deterministic analysis solution. So I'll see you in a bit.